SAC20B number 2. Get a magnet with a magnetic dipole moment of 0.65 ampere meters squared. It's in a magnetic field of 25 microtesla to the northeast. I've depicted that over here. And they want to know for what orientation is the torque exerted on the bar magnet by the magnetic field. Let's go ahead and put the bar magnet in there. Both clockwise as viewed from above and at its maximum value. Well, you get the maximum torque when the magnet is at right angles to the magnetic field. So let's stick that in there. Draw it at exactly 90 degrees to the magnetic field. So that's the answer for the orientation part. Probably ought to write that down. So A, with the magnet at right angles to it. Well, wait a second. We've got to make it so that it's clockwise as viewed from above. And put that up there, the north end there. Keeping in mind that the north end of a magnet is the end that we're to consider the arrowhead to be on. So that's the pointer. And then as the magnet tends to line up with the magnetic field, B, should I label that B, this will indeed swing around clockwise. And so it's this orientation, that is, with the magnet pointing due northwest. Magnet must be pointing northwest. And then, with the bar magnet in the orientation determined, what's the magnitude of the torque exerted on the bar magnet by the magnetic field? Well, we know, in general, the torque on a bar magnet by a magnetic field is equal to the magnetic dipole of the bar magnet crossed into the magnetic field at that location. And usually we think of that as mu b sine of theta. But in this case, since theta is 90 degrees, this is just 1. So the maximum value is always mu times b. And then we can go ahead and substitute those values in. I would say you can leave this part out, which is not so much analyzing it as recognizing that if the bar magnet is at right angles to the magnetic field, then the torque is just mu b in magnitude. In general, you have to worry about the angle. Technically, you could say here we worry about angle too, but when it's 90 degrees, sine of 90 is 1. Okay, mu is given as 0.65 ampere meters squared, and B, 25 microtesla. So the torque is, multiplying those two together. I guess I haven't done that yet, so let's try it. 0.65 times 25 equals, and it looks like I didn't hit the point there, 0.65 times 25 equals, so we get 16.25. That'd be micro Newton meters. Tesla is a Newton per ammeter, so it cancels out the ampere in one of these meters, and you got a Newton left and a meter, and of course you got the micro in there as well. I think I'll call it torque. It's rather weak torque. 16 times 10 to the minus 6, or 1.6 times 10 to the minus 5th Newton meters. Get to 2 sig figs. Okay, that's problem number 2.